Hello everyone. In this video, we are going to look at a specific block in Simulink that is very useful when you have subsystems or parts that operate at different sample times or different speeds. Okay, so let's say you have a control system here, although I have not really tuned it to do a specific task. But let's say the goal is you want the output of a physical system to match a reference signal, so your system is slow because of so many components in it, and it operates at a sample time of 0.1 or 100 milliseconds. Your sensor is faster, and it operates at a rate of 10 milliseconds. And your controller, which is done all in computer, is even faster, and it operates at 1 millisecond. So how would you make sure that when the systems working at different sample rates, they're working together, they're all doing their job the way it should, and no data is missed or no data is overwritten or anything, so the data integrity, we call, is preserved during the operation and the system is performing its job without being affected by these different sample rates? The answer is this block here is called the rate transition block. So if you just simply type in rate transition, this is a block that can change the sample time, and it can make the sample time bigger or smaller. In other words, make it faster or slower. So if you double click on it, it has some initial condition. It has output port sample time, which you can specify, inherit, or have multiple of that. And it has two checks, which are ensure data integrity and ensure deterministic maximum data transfer or maximum delay. So there are four things here that you need to specify or check, two of them and two of them specify. So let me tell you a little bit about them. The most important one is, of course, this guy, the output port sample rate, which it has to match the system that is going to accept it as the input. So for instance, here, if the signal coming from your sensor is 0.01 and it has to be subtracted from the reference signal. The reference signal is a signal generated in computer at 1 millisecond. The sensor is 10 millisecond. And so here you have to match this 0.01 to 0.001. For that, this rate transition block that you use, the output of it should be 0.001 because it has to come and be matched with that signal and subtracted to generate the error. Or where the error goes to the controller and comes out at the rate of 0.001 or 1 millisecond. Now, before it goes to the system, which only operates at 100 millisecond, you have to slow down, so the output is 0.1, right? Or again here, when the output of the system, which is 0.1, wants to be sampled by a sensor, which runs faster, you can basically run the signal faster, right? So output is 0.01. Okay, so you see the output rate is exactly the rate of the system that it is going to be used as the input. Okay, so that's the first thing. Now, if you look here, sometimes you make them go faster, sometimes smaller. Like in this case, you go from 1 to 100 milliseconds, so you're slowing down the system, right? But in this case, you're going from 100 to 10, so you are making it faster. And in this case, also, you're making it faster, so from 10 millisecond to 1 millisecond. Now, if you look at these two cases where you go from slow to fast, the label of the rate transition block becomes 1 over z. And what is 1 over z? 1 over z means what? Means a delay. Okay, so if you want to add some, this one. If you want to add some annotation here, you say 1 over z means what? Means delay, but the ZOH, which you see here when you go from fast to small, that is called zero order hold. And if you don't know what it is, I have a video published under my control playlist, which is about the basics of digital control systems. And I exactly explain for you what is a zero order hold. Okay, so if you want, just watch the video that is like the basics of digital control systems. I explain exactly that, and you can see why 1 over z is like a delay. Okay, if you look at the properties of Z transform, which I have a video on that as well. So that's the explanation of the symbols that you see on them. Now, this initial condition thing that you need to specify, do you need to specify it all the time? The answer is no. If you look at the properties or the description of this block in MATLAB, and if you go down to the initial condition, you'll see that only in one scenario you need to specify initial condition. And what is that? It says it only applies to slow to fast transition. If you are making the sample time smaller, if you go faster, then initial condition should be specified. Why? Because at the beginning of the transition, there is no output due to the absence of the input signal, okay? So the initial condition is only applicable when you go slow to fast, and for that reason, we can probably add that here, that initial condition is only applicable for slow to fast transitions. Okay, this you have to specify so that the people exactly know what you are talking about. Okay, so here we go. We got this. And now let's talk about the data integrity and the the deterministic transfer. What's the effect of these? If you check or uncheck these, what's going to happen to the performance of the system? And then we're going to run that and I'm going to show you everything. But first, let's look at these as well. So for that, you need to look at here, the effects of synchronous sample time. That's one thing. The other thing that is important is this part here, which shows the effect of those directly. So let me show you. So if you look, if I say I want to keep the data integrity and also the deterministic transfer function, if you select both of them, of course you're going to get them, but you have maximum latency. Your system is going to go slow because it has to make sure these two are exactly guaranteed. If you select the data integrity but not select the deterministic data transfer, okay, your latency is going to go down because you don't look at deterministic data transfer, but you need more memory requirement because you still have to track data integrity. And if you clean both of them, uncheck both of them, now you're going to have minimum latency and minimum amount of memory requirement, but guess what? You can lose some of the data integrity, and of course data transfer is not going to be deterministic. So you are at the danger of basically losing the original data the way they were and not get the performance that you expected. So it depends on what is it that is important to you, the fast Simulink running or the memory that you have, how much of memory, which is rarely the case. Most of the computers these days have enough memories, and if they don't, you're going to buy one and add it. But the latency could be important in real life, real-time applications. And but also the amount of integrity in the data is clearly the number one thing that you care about. And here is also the explanation of zero order hold and 1 over z. And if you uncheck those integrity or deterministic thing, you're not going to get a label for the block as 1 over z or ZOH. You get a level of a buffer. Okay, so your system now acts like a data buffer instead of zero order hold or delay. Okay, and you can see those as well here, that what kind of label you will get depending on whether your input sample time and output sample time are equal, less than, or bigger than, and whether you check or uncheck what those integrity and determinism. Okay, so depending on the sample times and those options, you're going to get a different label for the system. Okay, so just keep those in mind. Now here, what I did is just for one of these, I put a manual switch. So one time I run it with the data properly, the rate of it properly transition from 1 to 100 millisecond, and then send it to the system. And we're going to look at the inputs or the outputs of the system in this case. And another time I double click and I use the signal without changing the rate of it. So I use the fast signal and send it to the slow system. And again, we're going to look at the behavior of the system, these inputs and the outputs of the system and everything, and see if you can see any difference between them, okay? Whether we use this or not use this. Is that going to make any difference? Okay, so here we're going to do that. And we want to monitor some signals. We can either monitor them with the scope or we can monitor them with data inspector. So it's up to us. Right now, I put these two signals to be monitored by data inspector, but I can add these guys as well. So all you need if you want to monitor something with data inspector is you just right click on the signal, right? And then say log the selected signal. So you put this kind of like Wi-Fi symbol on it. And so now that guy will also be logged, so you can watch it here. And before you do all of that, one thing you can do is to click on this one here, this option. Okay, it's called sample time. This is beautiful. It can show you by colors and legends, basically, or labels, which signal has what sample rate. So this is really good. If you just click on it and say show all or show colors, look, then you get this table here. And then it says that, hey, any signal in red is what is 1 millisecond. Any signal in green, let me bring it all in. Any signal in green is what? 10 milliseconds. And any signal in blue is what? Is basically 100 milliseconds, right? So you can see that over there. And then if there is a multi-rate, any block that has multi-rates in it, in and out different, like this, you can see a different color. Now, one other thing that is important, look here, it says the sample model has 3 discrete rates, which is greater than the discrete sample time colors available. The third one have been marked, the third and slower rates have been marked using the same sample time color. Okay, so we used more than 3 apparently here. That's why there is a D4, and D4 and D3 are the same. And seems like for D4 we have a 1 somewhere, which I don't really see where. And if any system operates in continuous, then it is going to be in black like that. Okay, so here you can see, right, red is compared with red. Green is converted to red, right? Red is going to a system, and that's not really a good thing, right? Because this system operates slow, so you need to connect it to the blue one, so you really need to double click like that. So the signal is converted to the appropriate rate and so on, right? If I close this and do it again, right? So let me save this and run it again. Now it should show that you see here that the sample rate is basically reduced here. Okay, so you can see the sample rate and so on. And now I want to show you what happens physically. Is there any difference? So first, we're going to run it with slowing down the control signal to the system and run this thing. And now we can click on Data Inspector to see the signals. And then, as I said, we're going to switch. So that's my Data Inspector. And clearly here you see the difference between U slow and U fast. U fast, the control signal at 1 millisecond sample time is all of these spikes, but the blue one is what is clearly, if you can see, the blue ones are the slow version of input signal. Okay, or if you want, you can look at the outputs, right? So let me see if I can show you these and do an appropriate thing. So this is the behavior of the system, okay, where the yellow one is y fast and the blue one is y slow, okay. And y slow is actually, in this case, the output of the system, right? So look at the output of the system, how it looks like. Look at this kind of behavior that you have, of course. And again, clearly you see the difference between slow and fast, right? So this is y and u for this scenario. And then I'm gonna use the switch and run it again. And I look at this behavior again. And now you see that the behavior is completely different. Just look at y and compare it against what we had last time, right? So if I want to show you that, let me see. So if I can basically take a snapshot from this and copy it to clipboard and do it one more time with the other one. Let me show you. So this top one is with the, this bottom one is with the transition block. The top one is without transition block. And we have not changed any gain or anything. You clearly can see that the behavior is absolutely different in these two scenarios. So yes, it absolutely makes the system behavior different if you use or not use the rate transition block. And the answer is always use the transition block to make sure that everything is working properly. Okay, so that's why you use this block and how you can see these different basically sample rates, how you can monitor them with data inspector and so on, and the meaning of the parameters involved in this block. Hopefully it was useful to you. I'll see you in the next video. Thanks.